Yeah, thank you very much. A big thank you to the organizers, Thomas and friends, for inviting me to speak here and for putting together this wonderful event for all of us in this fantastic venue. I'd like to talk about work with Songju Lee and Wolfgang Lerche, and there's also upcoming work with my student Rafael Alvarez Garcia and with Songju, but I won't have too much time to discuss this. So the most will be about these papers from last December. So, as we all know, singularities play a major role in geometry and strings, and hence I think are a suitable topic for this conference. We all know that singularities in string compactifications are typically a sign of new massless degrees of freedom, and oftentimes related to enhancements of symmetry. This is so in many branches of string theory, and most prominently also in F-theory. As we all know, singularities over codimension 1 loci on the base of an elliptic vibration are in one-to-one correspondence with the gauge algebra associated with the 7 branes wrapping that locus. And mathematically, this goes back to the work of Kodaira and Niron, who classified for us the codimension 1 singularities of an elliptic vibration of a Weierstrass model encoded in the Weierstrass functions f and g, and the discriminant thereof are the various types of gauge algebras that appear in codimension 1 on the base of the elliptic vibration. And as you all know from this famous table, the Kodaira types stop in the classification once we hitch the non-minimal boundary when f and g vanish to orders 4 and 6 and the discriminant to order delta, discriminant delta to order 12. These non-minimalities have the property that if we try to resolve the elliptic vibration, if we try to resolve the singularity in the fiber, then this would destroy the Calabi-Yau condition. So we do not have a Crapant or Calabi-Yau resolution, and hence these are usually discarded, at least they are usually discarded in the F-theory literature. And once more, I'm talking here about singularities in codimension 1, not in codimension 2, on the base of the elliptic vibration. So the goal of this work from the point of view of singularities or of F-theory could be phrased like this. We would like to understand the geometry and the physics of these non-minimal codimension 1 singularities, and we'd like to bring them back into the game of F-theory, if you like. The long-term goal would be to understand this in all dimensions, in particular for Calabi-Yau threefolds and Calabi-Yau fourfolds. In this talk, I'm going to take a first step. I'm going to consider the situation of Calabi-Yau twofolds or K3 surfaces, which is associated with compactifications of F-theory to 8 dimensions. But you can view this as a starting point, I hope, for a longer program of investigation. And let me stress once again that we are dealing with non-minimality beyond Kodaira in codimension 1. Such effects in codimension 2 over codimension 2 loci have been studied in great detail, and we heard a lot about them also yesterday, at least implicitly. For example, the codimension 2 non-minimalities on a Calabi-Yau threefold are associated with certain degenerations at finite distance in the complex structure moduli space of the elliptic vibration. They lie at finite distance. We get new degrees of freedom. The new degrees of freedom are known to be tensionless strings, and they show the theory passes on to the description of a strongly coupled superconformal field theory in 6 dimensions. We heard about this yesterday. Blowing up the singularity then in the base would correspond to going to the tensor branch. And if you are interested in the many developments of this recently, then look, for example, at this review and many works therein. On the other hand, the codimension 1 non-minimalities, or beyond Kodaira singularities, offer very different physics. They lie not at finite distance in moduli space, but at infinite distance in moduli space. And as such, the motivation to study them is not superconformal field theory and strongly coupled physics, but on the contrary, weakly coupled physics in the context of the swampland program of quantum gravity. As we heard today already in Eran's beautiful talk, when we go to infinite distance in the moduli space of a quantum gravity, we expect an infinite tower of massless states emerging. This is the statement of the famous swampland distance conjecture by Uguri and Buffer. And in fact, it is speculated that the leading tower of such states should always have an interpretation as either a Kaluza-Klein tower in some dual frame, or a critical string tower, or some winding states of some critical string. This claim, in fact, holds for all types of infinite towers that one would get at infinite distance, so it's a natural question if this is also realized in this context of codimension 1 non-minimal singularities in F-theory. Moreover, the types of infinite distance singularities that we are going to study, while formally are in the complex structure modular space of the elliptic vibration, actually are of a slightly different type compared to those that have been studied in great detail in the literature already. Namely, we are interested now in infinite distance deformations in the open string modular space. After all, once we look at degenerations of your elliptic vibration, this is because 7 branes come together in a certain way. This is an open string modular space, quote unquote. Of course, it's tricky to distinguish complex structure and open string deformations in a fully non-perturbative setting. But morally, these are effects that have to do with the modular space of branes, in particular of non-perturbative branes. And so it's something that can only occur really in strongly coupled from the GS point of view situations. So in that sense, this study is complementary to previous work on understanding infinite distance degenerations in the closed sector, quote unquote, in particular complex structure and Kähler structure deformations. We heard about this in Aaron's talk, and here is a very incomplete list of some of the systematic studies that appeared in the past in the context of swampland physics. So let me give the 3 main messages that we learned from K3 and which we hope to also generalize beyond K3 to Calabi-Yau threefolds and eventually Calabi-Yau fourfolds. First, if we have a non-Kodaira singularity in codimension 1, then this means essentially that the compactification space, in this case the space with the 7 branes on it, this compactification space degenerates into regions with different types of 7 branes. So we will see that the compactification essentially separates fractionites into strongly coupled and locally weakly coupled regions. Second, there is a symmetry enhancement, as always when we have a singularity, but the symmetry enhancement is one to a loop algebra or an affine algebra. So it's not a finite enhancement like for the Kodaira types, but an infinite type of enhancement. And third, the infinite tower of states that go along with this symmetry enhancement have an interpretation as a Kaluza-Klein tower. They signal a decompactification in a dual, in this case, heterotic frame. These are the 3 main messages that I like to highlight, and the rest will just be now details and showing how this works explicitly for the K3 case. And then, as I said, we hope that this picture will persist with more complications also for Calabi-Yau threefolds and Calabi-Yau fourfolds. So the methods that we're going to use are fourfold. First, on the geometry side, 95% of the time we'll be dealing with a direct analysis of the Weierstrass model. This is the advantage that we have here since we are dealing with an elliptic vibration. We can put this into the context also of more abstract considerations and results of semi-stable degenerations and Kulikov models, but really the meat of the analysis does not even make use of this technology. From the strings point of view, we can compare the outcomes then to what we expect from duality via the heterotic string, and try to trace back the infinite degrees of freedom directly to string junctions as a realization of the affine algebra. And I'd like to highlight that, in particular, this point 1, which is the key player, and also point 4 will presumably carry over also to higher dimensional Calabi-Yaus. Point 2 and point 3 is something that is special to K3 surfaces and may or may not carry over in this way to higher Calabi-Yaus. Okay, so let's start. In this talk, K3 surfaces, so we have our usual elliptic vibration over a base. On the base, we have coordinates S and T. And we have an elliptic vibration in terms of the Weierstrass model of degree 8 and with functions f and g of degree 8 and 12 respectively, and 7 branes sit at the location of the discriminant delta equals 0. Now what we're interested in is, oops, now I have to go back. Yes. Now, what we're interested in is studying deformations of such an elliptic vibration. We, for simplicity, look at a one-parameter family of degenerations with a parameter u. This takes values in a complex disk. So we can think of this family of degenerations as defining for us a threefold whose fibers are the K3s at certain values of the deformation parameter. In particular, for u not equal to 0, we will just have K3s with usual Kodaira type singularities. And at u equals 0, we go to a beyond Kodaira point in codimension 1, as you will see. So this will be the central fiber of this threefold. And the goal is to understand what's sitting here in the middle. So we can do this very much hands-on because we have the elliptic vibration as a Weierstrass model. We assume, therefore, from now on, that on this elliptic vibration at, say, s equals 0, just some point on the base, we engineer a beyond Kodaira type of singularity. So this means that the vanishing order of f, g, and delta in our Weierstrass model at u equals 0, the deformation parameter, and over a certain point on the base s equals 0, go beyond 4, 6, 12. So we can do this extremely explicitly. F and g are parameterized in the usual fashion in terms of the two coordinates on the base. And each of these monomials comes with a certain polynomial in the deformation parameter u, and it can be chosen such that if we set u equal s equal, say, mu, we will have a 4, 6, 12 or higher singularity. What happens is clear. This is well known and was studied in the physics literature, for example, in this paper Aspinwall-Morrison, and then in many, many to follow. We can do a usual blow-up of the singular point. So we introduce a blow-up coordinate, E1. We go to the proper transform. We divide by suitable powers and find a new partially resolved space. The singularity at u equals 0 and s equals 0 cannot be present anymore because of Stanley-Reisner ideal relations. But on the new component E1 that we introduced, there might still be a singularity. And if there is, we have a non-minimal singularity. And if there is, we have to iterate the process and blow up further and further. And one can always do this until there are no 4, 6, 12 points left anymore. This one can show. And once we have done so, we will have introduced a certain number, say p, of blow-up coordinates. And our Weierstrass model, again, is given very explicitly as a polynomial, where now these prefactors of the monomials in the base coordinates s and t will depend on the blow-up coordinates in a certain way. So this can be done extremely hands-on, of course. And the result is, and this was already the first statement that I made, the result is that after these blowups, our Calabi-Yau threefold fiber, so this the fiber of the Calabi-Yau threefold, so these K3s, will now degenerate into a union of various elliptic vibrations. This is a union of elliptically fibered surfaces attached together. So each of these components here will now be a degenerate Weierstrass model by itself over a certain base. The base is given by the vanishing of the blow-up coordinate. We have p of those. So the base of this new elliptic vibration will be a chain of various base spaces. So we have separated essentially our 7 branes into different collections of 7 branes on different types of elliptic vibrations. And now we have to study what is the geometry of these various components that one finds. After p blow-up steps, we find a Weierstrass model for the total space, which may or may not have in its f, g, and delta various monomials in the blow-up coordinates themselves. In particular, if the discriminant has an overall factor of one of these blow-up coordinates, then this means that on the corresponding component, say this one, the elliptic vibration degenerates completely, degenerates everywhere over every point. So if one of these NP here is non-singular, is non-zero, then the elliptic fiber is singular over every point of this component. And how we have to interpret this is that this simply sets the background value for the axiodilaton on this component that we are talking about. Namely, the J function is related to the quotient of f cubed and the discriminant in the usual way, and this will take constant values over the internal components set by the appearance of the blow-up coordinates in front of delta. That's a question. Yes, they intersect. Yes, one can prove that they intersect like a chain. Yeah, this is a non-trivial statement, has been proven. In addition to this background value of the axiodilaton, we also have now further degenerations of the elliptic fibration over points. This is what we usually have in F-theory, points being the location of the 7 branes, in this case on the K3 surface. So now, in addition, we have various such codimension 1 enhancements on the individual components. These would be here these green or these blue dots, and these would be the physical 7 branes, which we have to read off from the restriction of this Fg and delta in suitable ways to the individual components. So that's the general picture that we expect. And before I give you the complete details of what can happen, let's do an example just to get some intuition. Our example would be a randomly chosen example. We choose with f and g in a certain way. So we have some polynomials in s and t. S and t are the base coordinates. And then we have a deformation parameter u. And I chose it such that at u equal s equal, say, mu, we have a singularity of type 4,6 in f and g, and it turns out 14 in delta. As it turns out, you do one blow up, you still have a singularity, you do another blow up, and then you're done. In this particular case, so you do two blow ups. So what you get is a union of 3 elliptic fibrations, or three degenerate elliptic fibrations, the original space, and then the 2 blow up spaces here. You read off that over the middle component, this one here with blow-up coordinate E1, the discriminant completely vanishes. So this means that over every point here, we will have an I2 fiber on the internal component. In addition to that, we have certain branes at various points. There are 8 branes on the left component, an E7, and 1 more on the right component, and furthermore, we have 2 + 4 branes sitting at the intersection. This comes just from reading off Fg and delta and looking for the singularities. Now, when these branes intersect or coalesce at the intersection of the components, the vanishing order is not well defined. At the end of the day, we would like to interpret these higher singularities as 7 branes, but we cannot read off the vanishing orders properly if they sit at the intersection of 2 components. However, one can prove that one can always find some base change to remedy this. What does this mean? Base change means that we replace the deformation parameter by a power of itself. In this case, the replacement u to u cubed in here would do the job. You have to resolve again. And what you then find is that after a larger number of blow-ups, 6 blow-ups, in fact, you find a chain with 7 components. The end components are the same. These are the 2 I0s. And this intermediate component here has now been replaced by this chain of 5 components with certain degenerations as indicated. And this can always be done, and it never changes the physical 7 branes away from intersections, so we would say that this is an invariant of the physics. One can always find such a base change, and it does not change the physics of the 7 branes which are located away from the intersections. So therefore, we can do such base changes at our pleasure without having to worry that this would change the interpretation of the physics. Okay, so this was just an example. Now let me present the results of this analysis. This can be done very systematically. We have to first classify the types of non-minimalities that can occur. So recall we have 4, 6, and delta vanishing to, Fg and delta vanishing to orders 4, 6, and 12 or higher. And there are now 3 cases, as it turns out, to distinguish. The first case would be delta is of order 12. Precisely of order 12, and not higher. As it turns out, when you do the blow-ups, then all the intermediate components will have smooth elliptic fibers over codimension 0. So we will only have the so-called I0 fibers, proper elliptic fibers, over all the intermediate components. This is the first case. Second case, delta vanishes to order bigger than 12. But F and G vanish precisely to order 4 and 6. In this case, all the intermediate components have so-called IN fibers. This means F and G do not vanish, but delta vanishes to a certain order. We have IN fibers generically over all the intermediate components. This means recoupling, as we are going to discuss in a second. So these first two cases are called, for reasons that become clear in a second, type 2A, and then type 3A and type 3B. And then there's the third case. Delta vanishes to bigger order than 12, and also F and G vanish to order bigger than 4 and 6. In this situation, the intermediate components have so-called unstable fibers. This means that we don't have an IN type, but for example, a type 2, type 3, or type 3 star, or whatever. However, again, it turns out that one can bring this into stable form by a certain birational transformation and base change. We will also discuss this more. So therefore, these further extremely non-minimal cases will not give rise to new type of geometries, but one has to keep in mind that they might also give rise to something that secretly lies at finite distance. I'll come back to this point later. So that was the classification so far. We have to distinguish these three cases. We know what happens in the middle components, and now all we need to know is what happens on the end components and patch everything together, and then we are done. Let's look at the first case, the simplest case, where the discriminant vanishes precisely to order 12. So all the intermediate components are just proper elliptic vibrations. And it turns out now that the two end components are also elliptic vibrations with each precisely 12 7-branes on it. So this means that we've separated the original 24 branes into 12 plus 12, both sitting on the two end components, and there's nothing left for the intermediate components. This means we can, of course, blow down the intermediate components to a point, and then we get something that we all know in the F-theory community. It's the famous stable degeneration that was studied a long time ago by Morris and Waffer in the F-theory context when studying heterotic F-theory duality. So this would be the situation where we only have the end components left. We contract all the middle components because there are no branes on them, and we have now two DP9 surfaces, so elliptic vibrations with 12 branes, that intersect in a torus. That's the case that is well known. But now what about the rest? Let's look at the so-called type 3. This means that the discriminant vanishes to order higher than 12. As we said, all the intermediate components have IN fibers. So the exodilaton on the intermediate components goes to the limit GS to 0. Why? Because the exodilaton can be read off from the J function, which is F cubed over delta. Over the intermediate components, F does not vanish, but delta does. That's what the statement is in those cases. So we get locally weakly coupled regions in the middle. There can be on top individual branes on these intermediate components. These would be of AK type, so they would also be 7 branes which are mutually local and give rise to extra SUN factors in the interior. And importantly, they appear only in the interior after, again, a suitable type of base change. One can also prove this. Now, what about the end components? There are two possibilities, it turns out. One is that the fiber just generically does not degenerate over the end components. This means we get rational elliptic surface with 12 singular fibers as before, as one of the end components. Or the elliptic fiber does degenerate. It will degenerate again to an IN, so F and G do not vanish, delta vanishes. We have local recoupling on this component, and we can have various types of branes. We can either have A-type branes together, which would give an SUN, or we can have D-type singularities. This would be a situation where F, G, and delta vanish to order 2, 3, and 2 plus K. These would usually, from K bigger equal to 4, mean that we have SO gauge groups. But here also, interestingly, lower values of K can occur because we're really in a weakly coupled regime, so we see fiber types that are not possible in F-theory at finite distance, but since we have here this local recoupling region, they actually can occur. And there are precisely 2 of those. Okay, so let's summarize all of this, all of what we've done so far. We have these 2 types of type 3 degenerations where the discriminant vanishes to order 12, to order higher than 12. In the type 3A case, we have n components both being rational surfaces. In the type 3b case, 3a case, we have surface n components both being rational surfaces, or one rational surface and one where the fiber completely degenerates. And in the type 3b case, the fiber degenerates completely everywhere, and we can only have A and D type branes on the n components. So the geometry is completely under control, and this is all that can occur. You might wonder, this is now just a quick parenthesis, how these different type of 3 cases are actually to be distinguished. The first situation, where the n components are rational surfaces, they come about if you just have a 4-6-12 or 4-6 bigger than 12 point and no further tuning. But you can do additional tunings. You can also enhance a weak coupling, so to speak, together with a 4-6 and bigger than 12 point. If you do this, you get the situation where you get one rational elliptic surface and one surface with generic singularity at the ends. And if you do this in a slightly different way, where the weak coupling limit wins over the 4-6 bigger 12 degeneration, you get a configuration of this type where the 2 endpoints are also weakly coupled. But this just as an aside. Okay, so this was the completely generic analysis of the possibilities. Now let's briefly put this into perspective of what is known in the mathematics literature on degenerations of K3 surfaces. There is a series of famous theorems by Kulikov, Persson, Friedman, Morrison, that every one parameter degeneration of a K3 surface can be grouped very roughly as into models of type 1, type 2, and type 3. The type 1 models are the ones in our context that would have Kodaira type singularities. So these would be situations where the K3 surface does not break up into various components and where the only singularities are just ADE type singularities or quotient singularities, ADE type singularities. This would be at finite distance and is not of interest for us here. The remaining ones lie at infinite distance in the complex structure modular space, Kolikov type 2 or type 3. In the type 2 case, we have different components that intersect over a torus. This is something that we already saw. And in the type 3 case, we get a configuration that intersects over a rational curve, if they do intersect. These are the general theorems on such degenerations. And this is for every K3 surface, not only elliptically fibered. For the elliptically fibered case, what was known prior to these developments is what happens for elliptic fibrations. For the type 2 models. Namely, for elliptic type 2 models, type 2 degenerations, one can only have precisely 2 types of such infinite distance degenerations. The first is the stable degeneration that we already saw, 2 dp9 surfaces intersecting over a torus. And the second, this is what we get when we have delta vanishing precisely to order 12. And the second possibility would be 2 P1 fibers that intersect nonetheless in a torus, which is the double cover of the base. This is essentially the situation where we take a Zen limit, a weakly coupled limit, without ever encountering a singularity beyond the Kodaira type. So the type 2 non-Kodaira singularities that we found, starting from 4-6 bigger 12, or 4-6-12, is what is called type 2a in this classification by Klinger and Morgan. And then in addition, there's the usual Zen limit. Okay, so this was known, but now to put our results into perspective, we give a classification result of the remaining type 3 degenerations, which in general are very complicated for general K3 surfaces. Namely, our result can be shown as stating that all elliptic K3 degenerations at infinite distance of type 3 must come from these Kulikov-Weierstrass models of type 3a or 3b, namely precisely these 3 types of possibilities that we saw. And this also fits quite nicely with very recent results in the mathematics literature, which essentially come to similar conclusions, but in a very different manner, and in a manner that I would not know how to generalize to higher n-folds, whereas this elliptic fibration analysis is, of course, something that we can always do also for the higher n-folds. I have, I think, 1 minute to just revisit this class 5, because I find this particularly amusing. So the intuition is that if you go beyond Kodaira, so 4, 6, or 12, 4, 6, 12 or higher, then you're at infinite distance in complex structure modular space. That's what I said, but it's actually not completely true, because there are also certain cases where nonetheless you are at finite distance. And these are what we called in the paper class 5. These are the situations where both f and g are vanished at order b bigger than 4 and bigger than 6, and the discriminant hence at order bigger than 12. If you do all the blow-ups, you find that on your intermediate components now, you get these unstable fibers. So for example, a type 2, type 3, or a type 3 star, or anything that would give rise not to an SUN type gauge group if associated with the 7 brane, but something non-perturbative. For example, in this model here, we would have a situation where we blow up with an intermediate component of type 2. But what one now has to do is, in order to bring this into Kodaira form, one has to do a sequence of birational transformations and base change. One can, for example, blow down one of the end components, like here, and then do a base change, and realize that then one is in a situation where one can do a proper blow-up to something that is again of type 2 or 3. But there are also cases where you end up with something of type 1, meaning at finite distance. Namely, this occurs when f and g vanish precisely to order 8 and precisely of order 12, respectively. So it's not, this intuition is not correct that everything non-Kodaira is at infinite distance. There are also finite distance situations, but after suitable base change, they indeed reduce to these 3 possibilities that we found. But that just as an aside. Okay, this concludes the physics, the mathematics part. Let's now go to the physics. So all we've seen is that there is this chain of vibrations where the extradilaton is essentially weakly coupled on intermediate chains, on intermediate components, and it may or may not be weakly coupled on the end components. So what is the physics interpretation? And in the special case of K3, we have at our disposal heterotic duality, so we can guess what the physics should be. Because for the type 2 degenerations, we know the result from classic work by Morrison and Waffer, because the type 2 degenerations are precisely what describes heterotic F-theory duality. This is the case where we blow down everything in the middle and end up just with 2 dp9 surfaces intersecting over a torus. And there we know that this is the limit where on this intersection curve we identify with the torus of the heterotic dual theory. And the limit is one where the scalar volume of this torus goes to infinity, while the complex structure stays finite. The complex structure stays finite because this torus indeed does not degenerate. It's just an elliptic curve. And this, of course, is a decompactification limit from 8D to 10D in the limit of large volume of the torus. So what about these unknown cases of type 3? Again, by the same logic, and as a result of the types of branes that we found in the middle, namely only weakly coupled ones, we are allowed to blow down everything in the middle. This is a non-trivial statement that we can do this because, and it's a consequence of this local recoupling. When we do this, we again find 2 components, and the curve, and they intersect over now a singular curve, essentially because at point P, all the intermediate branes have been coalesced, but they are only A-type branes, so the fiber over this will just be a pretty harmless fiber with a nodal singularity. And again, we can guess that this should describe compactification of the heterotic string on a dual torus, which now has pinched, so has degenerated. So we not only take the limit t to infinity, the scalar volume to infinity, but also complex structure to infinity of the dual torus. And this means that since now the ratio of the heterotic scalar modulus and complex structure modulus in fact stays finite, this is effectively a decompactification from 8 only to 9D. We get only 1 tower of states. And this intuition can in fact be confirmed quantitatively by using the map between the Weierstrass model coordinates and the dual heterotic string. These coefficients of the Weierstrass model can be related via certain Siegel modular forms, at least in certain cases, and we indeed confirm this intuition. So this already gives us a guess based on heterotic duality what we expect. So if these complicated degenerations are really nothing else than a decompactification in a dual frame, then this means that we should find Kaluza-Klein towers becoming massless at these degenerate limits of complex structure moduli space. The states which we expect from an M-theory point of view should correspond to M2 branes wrapping certain vanishing curves. Or equivalently, in the context of, in the language of F-theory, we would expect string junctions wrapping around certain of the degeneration points an arbitrary number of times such that we get full towers of states. Let's first practice how this should occur in the type 2A models. These are the ones dual to usual heterotic decompactification. Again, this is the situation. Where now would we get a vanishing 2 cycle from in order to wrap M2 branes? Well, clearly we can fiber the 1 cycles on the torus over which the 2 components intersect over one of these pinching cycles sigma, which pinch at the intersection point. This will give rise to 2 tori, 1 2 torus from sigma b fibered over capital sigma, SB fibered over capital sigma, this one here, and 1 from SA fibered over sigma, the second point here. These are 2 tori, they are elliptic curves, so we can wrap multiple times, infinitely many times. We get states which become massless because the cycle sigma can be shrunk to a point. So these are the 2 types of states that we find, and the important message is they are nothing but KK towers in a dual frame. Even though they may not look like it here, they are KK towers in the dual heterotic frame. From the F-theory point of view, these are nothing other than just string junctions localized at this intersection point. So an M2 brane on this first torus corresponds to a 1,0 string, an M2 brane on the second to the 0,1 string, because these correspond to the 2 types of 1 cycles in the fiber. They can encircle all the 12 7 branes, say, on the left. The monodromy of those is precisely given by the inverse of the monodromy around this point P if we go along sigma. This is since at the intersection we have a non-degenerate torus, just an I0, so just the identity, we find 2 eigenstates, and these are precisely the 2 types of Kaluza-Klein towers. And more mathematically, this means that the 12 7 branes on the left, in fact, enhance from a maximal E8 possibly into a double loop extension of E8, the algebra het E9. So we have an enhancement to a loop algebra, in fact here a double loop algebra, and with it comes an infinite tower of states from the roots associated with this double loop algebra, and these have an interpretation as KK towers. What's true for type 2 is also true for type 3, just that since we are now intersecting over a singular curve, we will get not 2 towers but just 1 tower. Because of the more complicated monodromies, we can indeed only fiber, for example, the 1,0 string, but not the, only fiber, say, the SA curve, not the SB curve, over the sigma. The other fibration is forbidden by the non-trivial monodromies. And one can convince oneself that in this way one finds the affine node of a single extension of whatever gauge algebra one had originally. So in this way one realizes the affine algebras had E9 minus n, where n corresponds to the type of degeneration at this intersection point. And this is precisely what enhances, what signals now a decompactification from 80 to 90 in the dual heterotic picture. More systematically, the symmetries, the symmetry algebras that we find in this way are therefore of the following type. We can have 1 or 2 affine factors from the 2 end components. 2 of them if we have 2 dp9 end components, 1 of them if we have only 1 dp9 end component. And on top of those, we also have a possible finite gauge algebra. This is whatever comes from the intermediate components, but this can only be of perturbative type and easily read off. And in particular, as a check that this picture and interpretation is correct, one can try to find from this the possible maximal non-abelian rank enhancements, gauge algebras in this way, and compare to what is known to be the non-abelian gauge algebras of maximal rank in 9 dimensions. And for the rank 17 case, which is the one that we are considering here, this will lead to 2 types of series. This first series, if we have only if we have two DP9 end components, and this series here, if we have only a single one, and this precisely matches the previous classification of these highest rank algebras of rank 7, of these maximal non-abelian enhancements in 9 dimensions. And I should also mention that the case where you switch on fluxes in addition to geometry was treated in this nice paper by Svetic, Dirigel, Lin, and Zhang, and it leads to a classification of the second branch of possible maximal gauge enhancements. Okay, I should probably skip this in the interest of time, and instead would like to conclude. We've started a classification of infinite distance deformations of the elliptic fibration as such in F-theory from a systematic point of view by first looking at the elliptic K3 surfaces, and tried in particular also to gain their F-theory interpretation. We find essentially 4 quantitatively different cases. One corresponds to a total decompactification from 8D to 10D. One corresponds to a straightforward recoupling limit. This has nothing to do with non-Kodaira singularities. This is just the Sen limit and needs to be included for completeness. And then we have these 2 type 3 limits, which were not known before. One is a decompactification from 8D to 9D, and one from 8D to 10D in a weakly coupled regime. I didn't have time to discuss this latter one, but I'll be happy to if you ask me. So as I said, this would be the first step. The work in progress deals with generalizing this to elliptic Calabi-Yau threefolds with non-minimalities in codimension 1. And much of what I've shown persists, so we still find a modular separation of the compactification space into regions of constant coupling, up to, however, codimension 2 effects, which complicate things. So this leads to a considerably richer structure, but we believe that with these techniques we can also tackle those, and I hope to report on them next time or soon. Thank you very much for your attention.
Thank you, Timo, for this very nice talk. Other questions, please?
Yes, very nice talk. So, just a comment. I think you probably fixed the area of the P1 base, or you did not take.
Exactly, we not take a limit.
But if you had done that, I think if you kept it big rather than small, then you would, instead of getting heterotic, you would have gotten type 1 prime when you went
very good.
To 90. In that case, which is just the case that we had studied with Freddy,
exactly.
We had gotten a case where you had real elliptic.
Right.
I do
not. I'm well aware of this. I do not see this real structure. I think these are probably 2 different ways of looking at the same physics, essentially. So reality means that there is indeed a degeneration, a very bad degeneration, and this degeneration here in this algebraic point of view seems to be regularized to the extent that that instead of degeneration everything, you split up your geometry into these modular pieces, which then intersect over these normal crossing singularities.
My question better. If you go from 9 to 8, there's a momentum. You can in principle flip the momentum. The reality structure for us was that flip.
Mm-hmm.
So there must be a reflection of that Z2 in your language too. If you're saying that 9D immersion, there must be a Z2 which does that.
There might be such a structure, yes. Yes. Would be interesting to understand. Thank you.
There was another question. Yeah. In the threefold case, I have 2 questions. First question is, are you assuming bases which are P1 fibered?
No, not necessarily. For the so this is the one that we start with, of course. For the P1 fibration, one can find a very similar pattern, even though this is already, nonetheless, because of these codimension 2 effects, quite complicated. But no. Then you have a local. You have this modular structure now becomes a local statement. So at the end of the day, we will not want to assume the P1 fibration.
Okay. And the second question was, can you maybe say a couple words about this caveat up to codimension 2 effects?
Yes. So, for example, in the P1 fibered case, so what can happen is that even though you have you can have you can have non-Kodaira singularities over various curves, and then you get this after this blow up, this modular structure. But they can of course also intersect, and then you need to deal with those singularities.
So it's not clear, I guess, how to interpret.
The interpretation might, in some cases, the interpretation is clear, and in others, it's not yet. Yeah. But this is something that needs to be worked out.
There's another question here that comes, please.
Did you look at the relation to the kind of limiting mixed Hodge structure story? Because you even use the same notation now. So it seems like that kind of these various limits which you give correspond to kind of what we call enhancement chain.
Yes, so this is exactly this year. So for K3, of course, this had been done long ago by these mathematicians, these various types of Kulikov degenerations. The type 1, 2, and 3 is this Kulikov notation that I'm using here. And that was the point of the slide, to show that indeed it fits into this general classification, and is a refinement of that classification, in fact, because these type 3 limits now come in various classes, type 3a and type 3b, and they have very different physics. So one lesson that I'd like to draw from this is that this Kulikov classification into 1, 2, and 3 is not yet sufficient to tell you about the physics.
That's why we introduced these enhancement checks. So we started kind of saying that the single type is not enough. So you need to also kind of specify how you approach.
Right, but this is okay.
Is that also what you find?
No, because we do. I'm not sure. So this is not about taking like multi-parameter limits, or not seeing how we get there. But these are really. So the point is, in this last class here, the states that one gets from wrapped M2 branes does not exhaust the possibilities of towers. That's the problem. This type 3, at first stage, it would look like, if you only look at wrapped M2 branes as giving rise as the source of KK towers, you would find one such tower, because it's type 3. But the physics is really a compactification to 10 dimensions, so you get 2 towers. There's another tower, which is a dual actual supergravity tower. This is what I skipped over. Maybe I shouldn't have done that on these last 2 slides. So one finds actually 2 types of towers. One is the one that one expects from the wrapped M2 branes, and then additional states that one doesn't see in this way. So that's why this type 3 really has more towers than the limiting Hodge structure analysis as such gives you. That's why I think this goes beyond that in that sense. So it's really, it has 2 towers, even though it's type 3. Limiting Hodge structure would tell you get 1 tower. But this is the subset of towers that you get from in this case, M2 branes wrapping, vanishing, in this case, elliptic curves, right? These additional states will be Kaluza-Klein states in the dual compactification. So here it is in a dual picture. Here it is actually very simple. The interpretation is we take a weak-coupling limit first, and then on top of that, 2 pairs of O-planes come together. So this means that first we go to globally type 2, so type 2b, globally type 2b, and then we put 2 O-planes together on pairwise, and this means that we will get new states. But geometrically, it means that we take also the large complex structure limit of the type 2b orientifold torus. So it's a type 2b limit, including also large complex structure. And this gives 2 types of states, because the torus goes to infinite complex structure. One is a winding tower state. These are precisely the states that we see here from the wrapped M2 branes and also from the general type 3 predictions. And the Kaluza-Klein states, these we know in this case to be present because of this simple picture, but we do not have a good handle on them here.
Now you say that the type 2b limit n is kind of weak, so this is a 2-parameter thing.
It's one parameter. I'm not sure how to.
That's what we count as 2 parameters, because they're also independent limits. So you could put
Fine.
them in order.
Fine. Yes, okay, good. But the end, yes, okay.
And then this gives you kind of a chain of enhancements, and there are now two possible chains, and therefore there are two possible.
Right. These are the type 3A and type 3B, if you like. Yes. But the important point is we get one more tower. So that's really what I want to stress. It's one has to be very careful when how to get these towers, and these might only be a subset. And I think for the physics, this is very important.
All right, there were two hopefully very short questions. Fabian and Paul, or do I can ask privately to them? Okay. Paul?
Just really quick. I was wondering, can you also, these degenerations, can you also express them in terms of the cell-dual intersection form on the K3? So if I could, for example, if I say I generate into an elliptic curve or so, then there's certain polarizations in my K8 lens or so.
Yeah.
Or if I go to lines and I generate a U with
Yes.
K8.
Yes.
And that would also sort of, or sorry, something like this, such a presentation would also.
Yeah, this would be closer to this usual way of approaching this in the mathematics literature as it has been done in these Kulikov papers. Absolutely. And the various towers then correspond to these hyperbolic sublattices. Indeed.
All right. I think we should continue. So let's thank Timo again for his nice talk.
Thank you. Geht's dir gut?